All right, today I want to talk to you about something that I'm going to coin the term for. I call this the rock skip effect. You're thinking, well, why are we talking about skipping rocks to VRF? Now, as you can see, I've got operational data here in front of me like I always do almost every day. And I thought I could actually make this video while walking on my office treadmill at the same time. Come to find out that that was actually really hard to do. So one of these things here is not like the other. In this specific system, there's a lot of different areas that we can focus on when looking at operational data as a whole. And with something like this, when I say the rock skip effect, let me explain what I'm talking about here. We're talking about saturation temperatures. They're a determination of whether something is a vapor or a liquid within a refrigeration system. In something like VRF, that might be constantly changing, especially if settings have been turned on that allows VRT to be turned on, which makes the refrigerant saturation temperature change based upon ambient, which I'm going to show you here. So let's peel a lot of these things back. We know we're in full cooling mode here, so we take that off the board here, right? Discharge pipe temp. We don't need this one. Compressor is not running. The discharge pipe temp here, we'll keep it for the sake of what I'm about to talk about. Suction temperature, that's always an important one, right? If we're going to suction superheat. TC, don't really need it. I'm going to take it off the board here. Inverter rotation amounts, right? We know the compressor is running. I'll leave that here just because we have two gaps here. Again, there's another compressor here. 3 modules. You're asking, what modules we got here? 3 modules. As you can see, there's a compressor running from here all the way back over here. They're just cycling between compressors. But the rock skip effect. Let me take away the compressors here, okay? And take it all off the board. Otherwise, you guys are going to be like, what the hell is this guy talking about? It's driving me bananas. Okay, taking this away. Last but not least, there's one more in here. Where the heck are you? Oh, that's my, okay, no, that's supposed to be it. All right, so we're gonna zoom in some. Oh, that's actually zoom out. Don't listen to me. Okay, move over. It's not as good as I thought it would be at this zoom. Okay, let me take some things off the board here. Some more, keep going. And then we'll add this back in for the sake of argument. Okay, rock skip effect. Here we go. So you can see here, this is my suction temperature, my saturation temperature of my suction line, right? This is my suction superheat. Now you can see here that my saturation temperature, which is purple at the bottom, is doing this, right? You could call that the wave motion if you want to. Yeah, you didn't know I had moves like this, but I actually do. No, I don't, I'm just kidding. But the rock skip effect is essentially this. When you throw a rock across the glass water, right? Perfectly level, clear, which is what we have back here, you'll find that that rock does what? It skips across the water, unless you're really crappy at throwing like myself. But in that case where you see this up and this down, okay, that's normal saturation temperatures. Well, normal compressor changes that are going up and down, and the saturation temperature is going to modulate because the compressors are what? Modulating. Okay, we're all on the same page here. But if we move forward in the data, you're going to find this. The rock skip effect is this. When you throw a rock across the water, what happens at the beginning? Well, at the beginning, it clears the water pretty far, right? It hits the pond, and then it skips off, and it goes up high. And then it hits the pond again, and it skips off, and it hits up high. And eventually, at the end of that cycle, it eventually will what? It'll get closer and closer and closer to the water until eventually it falls in the water. And that's what you have here. In this saturation temperature, we have suction superheat that's within a normal range. And then we see here that it gets closer together, right? It hits the water and then it bounces off. And then it hits the water and then it bounces off. And then we come back where we're in low suction superheat for an extended period of time here within this data. Now you say, wait, okay, so where's the liquid? Is it floodback? Is it a failed subcooler? Is it indoor units that are bleeding by? And it's none of those things. So what would cause this effect in a system where we have low suction superheat here, we have low suction superheat here, we have low suction superheat all through here, right? All this data here. It's somewhat low here, it gets even closer, and then it goes back down again. What would cause something like that? Well, what you'll find in refrigeration systems is specifically VRF. If we go and we actually plot, and the data got pulled in wrong on this one, and that happens, it's okay. We go into our target evaporating temperature. This is the target that the system is trying to match within the unit. You'll notice here that when the water was nice and clear and level, you'll see that it turned down the saturation temperature by a lot, like a little bit here, 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 and then it goes back up again, okay? So this dip in the system is the system saying, hey, here's my indoor unit demand, and I'm taking that indoor unit demand and I'm saying it needs this much capacity. And so it's using the target evaporator temperature to drive the compressor to get it to manually do what it wants to. And then it realizes, okay, well, that we don't really need that much demand after all in the system. And so what does it do? It raises it back up again. You see here, we started at a saturation temperature of 51 and we landed at a 50.8. And so it went down and then it went back up. And in those changes in saturation temperature from the target, usually when VRT is on is when you'll see things like this.
There's that dip and driving the compressors to run, driving to move the refrigerant inside the system at a specific speed has an adverse effect. And the data, as you can see, where the liquid refrigerant is just too much. And so what happens to the indoor units when it changes saturation temperature and it hasn't balanced out yet? It looks like we have floodback, and we technically do, right? If you lower the saturation temperature and drive your compressors to, let's say, 40 degrees, and then you turn around and raise it back up to 50 after the compressors get running and the refrigerant gets flowing and it starts moving and it starts going through the indoor units, what do you think is going to happen when you raise that saturation pressure and saturation temperature on the outdoor unit? Well, the compressors are going to do what? They're going to slow down. And when they slow down, the refrigerant's still moving. We're still getting some, low temperature refrigerant and liquid back on the suction line. Because we've changed the saturation, now we start to flood back, which is what you see here. So this isn't a particular issue because as we go, if it continued, then yes. But you can see the wild fluctuations that we have here in those temperatures, right? This is changes in saturation, pressure, and temperature. The target's constantly changing. This is what you'll see with VRT turned on in a lot of systems. It's not just the matter of, okay, where's the liquid coming from? Maybe it's overcharged, and this system actually isn't overcharged. It actually might be a little bit undercharged. But you'll notice that when you move the goalpost on VRF systems, you can't just snap judge quick, say, yes, that's exactly what it is. If my suction temperature was 50 degrees and my saturation is 40, but then 2 minutes later, my saturation temperature is also now 50 and my suction temp is still 50, well, guess what? It turns to a liquid. It is a liquid, right? And if it changes even more adversely where the suction pressure goes to 52 or 52 degree saturation on the suction line, and my suction temperature is 50, I'm now subcooled it to 2 degrees, right? And so it's those things that you're going to find in refrigeration systems like VRF that you have to be slow to play, which is why we talk about zooming out like we do. And you can see here between all the data, it kind of levels out eventually. And obviously compressor speed dictates that. You can see where it probably turned off, compressor discharge goes down, and then it goes back up again here. So if I keep going through the data, you can see that. See the squiggly wigglies here? Yeah, that's a scientific term in case you're wondering. Those are all conducive with what's going on in the system. And so if I want to go back and I want to take this away, and you'll notice that the valves are at low pulses, the demand in this building is really low. I'm not happy with any of that at all. Let me see here. Where is my target evaporating temp? Got it off already. Okay. Yeah. And so if I take away my discharge compressor temp, this is my suction saturation and my suction temperature. This is my suction superheat. And you say, well, there we go. We touched here. But you'll also find too, like systems that have like non-condensables in them, you'll find where the data on something like this mirrors the fluctuations, where they're always out of sync, where one goes down, the other one's going up. But then as this one comes up, the other one's going down. I've seen that in a lot of data. I'm actually gonna make a video about that here soon. But those exact things all kind of play a part here. And as you can see, that's all I wanted to say. Just VRT will get you sometimes if you're not looking for it. VRT will also mess with the operational data that you look at. You'll find that, something like this, if it were to get to that modulation where it landed at zero suction superheat here, and it stayed there and the demand was still on, and I would go looking for the liquid, I go looking for the overcharge. But for this, the demand is just so low. This is what you see when you start up. This is also why you can't look at operational data in such a short period of time and make a judgment, make a decision. That's why we don't like 20 minutes of data. That's why we don't like, an hour of data. If it was up to me, I would have, 10 hours of data. This is actually 89 hours of data. So careful what you wish for. But again, these are small things that you have to look for and rule out in your own mind when you're looking at operational data with VRF systems. This isn't just Daikin systems. This may be Daikin Service Checker, but this has to do with all VRF systems. It's that constantly changing goalpost. It's compressors constantly changing speeds, and then evaporators just doing what they have to maintain a 9-degree superheat. When you put all of those together in a 20, 30, 40-minute cycle, you have to understand that things have to settle, which means compressors need to stop changing speed drastically, which means 1, 2 RPS up and down, 3 RPS up and down, that's okay. But when we're looking at swings, like what are we talking about? Let me show you. Like this. Drastic changes in speed. We're way up high, and then we're way down low, and then we're way up high-ish, half-ish, and then we're down low again, and then we're up high again. We don't want to see any of that. We want to see sustained normal operation. Now, you'll see that this is a triple module, so it might rotate between compressors or it might rotate between modules, and that's a normal operation every 20 minutes. That happens at VRV4. That's normal stuff that we usually look at. You can see here when we're doing that, where this compressor is run for X amount of time, and then it's going to turn around and switch over. Now it's this compressor's turn. Well, guess what? Now the demand is not there. They both turn off. Then guess what? This one turns on, and that one turns on, and back and forth, back and forth, back and forth, back and forth. We can go on all day about that. But again, this is just to show you that things have to level out within the system. The demand has to be equal within the system to understand if what we're looking at is something I can actually make a decision on. Can I look at suction superheat and make a decision based upon that? Can I look at discharge superheat and make a decision based upon that? Can I look at system subcooling and make a decision based upon that? In this small snippet of data from here to here, I can't make that decision. I can't say if it's overcharged. I can't say if the liquid coming back is because of a lack of heat exchange at the indoor units and dirty coils or dirty filters, which I would love to because it kind of looks that way in this data. But then when you go back to also the saturation temperature, when the saturation temperature is constantly changing on the system, the target, I can't really make any decisions because everything is moving too much. Everything is modulating too much. Everybody is doing their own little dance to their own little beat. And because of that, there is no consistency, which makes troubleshooting data like this even harder because now you have to find that small window at the heat of the day where there was enough demand on the system, where there's enough stabilized operation that I can actually look at those three things to make a decision. Those three things are not what you can hang your hat on every single time. So there you go. Rock skip method, call it whatever the hell you want to. Bounce method, squiggly wiggly method. I mean, it's whatever you want to say. It's just to tell you that there are too many variables moving within a natural system to then just look in and hone in on low suction superheat. Because when the suction superheat was low, guess what? The discharge superheat was also low here. If I go and I look at that, you'll see the discharge superheat go like this. So we know there's liquid there. But also, there's more to this video, obviously, even though I wanted to end it a while ago. There's more to this because when we talk about small instances like this, if my system is set up incorrectly, if my system is applied incorrectly, application matters. When I say applied incorrectly, that just means that the space that this serves never has a real heat demand, never has a real heat load. The way they're using this office isn't the way that it was originally designed. Maybe the DOAS system has changed. Maybe someone changed the discharge set point on the DOAS for the air that's coming into the return air of these units that's derating the coils. Maybe there's bigger things that we're not seeing on a system like this that can cause compressor failures, can cause oil return. When you look at a system like this and you see these squiggly wiggly lines where the saturation temperature and the suction temperature are modulating like that, where the saturation temperature set point is also modulating and the compressors don't settle out in normal operational windows, then you have to look at this and say, okay, how many times does this happen a day? Because if this happens 9 times a day, is that enough to kill a compressor? It is over 2 years. It is over 3 years. It is over 5 years. Those things play a bigger factor in a lot of this stuff. It's not just did it have wet operation and liquid getting back to the compressor? The answer is yes. How often? Because if it's only happening once every 7 days, then I'm not that concerned, right? I'm going to look at other things. I'm going to look at other operational data. I'm going to ask you to stress test the system and record it and let me look at it. Those are things that I'm going to do. But if I see this happens 10 times a day, right? And you're telling me you've lost 6 compressors in 7 years? Well, yeah, no duh. Yeah, you lost compressors because you keep flooding it in small increments throughout the day. It's enough to where this is a slow wear, right? This is a slow wear of all the bearings within that compressor. This is a slow wear of the scroll plates. This has long-term consequences on a system. It's not designed to compress liquid, but it's also not designed to compress liquid during normal operation, even when the system is set up correctly because it's being misapplied, right? And when the misapplied part comes in is again, like the things I mentioned. All those things play a factor in troubleshooting VRF as a whole, but this is one of those things where you can look at it and know, okay, what is this doing? How is this changing? And I've even told guys too, where maybe they want the VRT turned on, and that's okay if that's your climate and it works for you. If you're there to stress test the system, I'm turning VRT off. I don't know about you, but I'm extremely impatient with systems like this. There's already enough, startup control mode, pump down residual mode. Modes drive me crazy. I just want you to run the way I want you to run and stabilize so I can look at it. And that's it. And so if I have to go in and set the saturation temperatures both on the condensing side and the evaporator side, if it's parallel operation or if it's heating operation or cooling operation, I will while I'm there. I'll change it back. But for the most part, you need to understand how the settings are set and applied to understand that maybe the data that you do record is 89 hours, but it could all be garbage. And I hate to be that guy to tell you that, but it can be. So these are all things you need to think about. Hopefully you found this video entertaining, and I will see you guys on the next one.